This session is going to talk about air quality modeling and how it can be used for, again, framing clean air action plans. For this session, the moderator is Mr. Kaushik Muduchuru. He's a senior associate at the Atmospheric Composition Modeling Group at the Air Quality Sector in CSTEP. For panelists, we have Dr. Sarath Guttikunda, who's the founder and director for urban emissions. Dr. Sachin Gude, scientist, FD, IITM, which is Indian Institute of Tropical Meteorology. Professor Srinidhi Balasubramaniam, who's the core faculty assistant professor at IIT Bombay. Professor Dan Westervelt, who's a professor at Columbia University. And Dr. Piyush Bhardwaj, who heads the modeling group at Air Quality Sector in CSTEP. Kaushik holds a PhD in climate studies with a focus on aerosol cloud interactions. He has previously worked and has experience in sustainability and physical climate risks. His current interests at CSTEP include research in black carbon mitigation strategies and air quality modeling for policy research. I now hand over the mic to Kaushik to take forward the session.
It is my pleasure to welcome you all to the air quality modeling for improved clean air session. So we have a distinguished panel here who's going to talk about the latest advancements, methodologies, and applications of air quality models. First, we'll have Professor Srinidhi, who will give an overview of the CTMs, then followed by Sharath and Piyush, who will speak on the airshed approach. Then we will have Sachin Gude sir, who will speak on forecasting, and then we'll have Dan Westervelt, who will end the session with the multiple benefits, climate co-benefits. So we'll first have Professor Srinidhi Balasubramanian. So Professor Srinidhi Balasubramanian is an assistant professor in the Environmental Science and Engineering Department and affiliate faculty at the interdisciplinary program in climate studies at IIT Bombay. Her interdisciplinary research interests are in developing and implementing air quality models for the study of human and ecosystem health, sustainability of agriculture and food systems, and indoor air quality. She has a PhD in civil and environmental engineering from the University of Illinois at Urbana-Champaign, where she developed agricultural emission inventories and air quality modeling. She'll hopefully speak a lot more on ammonia. She did her postdoc research at the University of Minnesota on air quality applications in the global food systems.
Hi, good afternoon, everyone. Welcome to the post-lunch session. So thank you for the lovely introduction, and big thanks to CSTEP for having us come over here and share our work and thoughts and opinions. So I'm an air quality modeler by training, and invariably the question comes back to, should we believe you and your outcomes? And I think it's a very valid question, right? Measurements are considered reality despite its uncertainties. Models are considered to be wrong despite the skill and its strengths. So that's something I really want to touch upon, is a detail which matters most to establishing the skill and capabilities of a model, and how what are the different ways that could have been done. And then there's something that we proposed as a part of a recently submitted piece of work from my research group. So there we go. So just as a general overview, we've seen source apportionment, we've heard a lot about measurements, but really at the end of the day, the idea is mitigating air pollution, maximizing gains for clean air, and fundamentally one needs to establish what I call the causal chain. Where are the emissions? What are the emissions like? What is the role of transport and chemistry? Dominant for certain sources, perhaps less important for some. Chemistry extremely important, what's happening, what seasons, what time scales. And use that understanding to create what I call gridded concentrations, across space and time of important air pollutants. So you don't need to model everything, but if it's something that impacts health, like PM2.5 and ozone, impacts ecosystems, again, PM2.5 and ozone, it's really important for us to know what their trends are, and then where are the receptors and how differentially are they getting impacted. And really, once you have an understanding of that, the mitigation angle becomes a little more straightforward to resolve. But mitigation is also scale dependent, right? Who needs to be impacted where and how is also a function of who can enable such mitigation. So one way to establish the causal chain is by what I call a first principle. Oh, it doesn't go backward, is it? There we go. A first principle approach. Now, in many countries, regulatory models are usually dispersion models, which are based on Gaussian plume principles, but you can use first principles to be modeling a chemical reactor, which is basically a single box in which all kinds of atmospheric processes are happening. And as a quick primer, this is what boxes look like. There's pollutants coming in, pollutants flowing out. There's, of course, emissions within the box, chemical loss, chemical gain, and also deposition that is happening within the box. You put a series of these boxes together along, the 2D horizontal and the 3D vertical, and voila, you have a mathematical foolproof, kind of quote-unquote, foolproof approach to be able to get those spatial temporal trends. And CTMs have been vitally, chemical transport models are just a fancy way of calling an air quality model with very strong chemistry representations in it. So CTMs, which are first principle powered, can help us discern source receptor impacts. Then you can use those relationships for ecosystem and health assessments, like we saw in the global burden of disease maps that some of our speakers earlier today showed us. For validation of emission inventories, you can backtrack information, use inverse models to constrain the reality of your emissions itself. And for forecasting and decision making. In fact, when I tried reviewing the NCAP documents, CTMs were largely mentioned in the perspective of forecasting, and that's been successfully implemented through SUFFER and similar systems in places like Delhi and I believe Pune and Mumbai as well. And of course, perhaps eventually for regulatory purposes. So CTMs, of course, are only as good as the representations within the model are, and only as good as the inputs that are fed in, right? Bad data in, bad data out. Also, limited parameterizations, meaning limited resolution of how you describe the math of the chemistry and the physics also limits the ability of the model to predict correctly. So, this is a famous quote. I'd like for that to be at the center of what you take away from here. All models are wrong. Some are useful, and that the approximate nature of the model must always be remembered. Knowing this, how do you then use a model? One, we want the model to be correct, model veracity. The second is we want the model to be diverse, meaning it could have not great outputs, but it could still be very useful, model versatility. Today's talk, I'm going to kind of focus just on the first part. How do you establish model veracity? How is it a correct model to use? So to what extent do you want to believe really this imaginary outcomes from a mathematically constrained system, right? And the way we go forward is called operational evaluation. So what you do is you take predictions from the model and you compare it with reality. And, reality could be samplers, which has been a large focus of our clean air efforts across the country, be it research, be it policy, be it anything else, to expand our capabilities to measure. You can compare these model outcomes to ground observations taken at different locations, different times of the year, satellite measurements, aircraft measurements, name it, measurements as an indicator of reality. So you statistically compare predictions to the observations, and then you see closure. How close are they in magnitude, and how well are they replicated across, a series of setups, so association in trends as well. Unfortunately, What we have seen so far is people don't always use the same set of metrics. And this becomes a challenge in a data sparse country like India, where our regulatory observations are not as, it's not a very big data set like it is, say, in the US or Europe. So we are data constrained. And in this data constraint, we are also constrained in how we report. We do not consistently report the metrics. So, your answer and my answer could both be correct, but they could look very different. So how do you then compare our perception of closeness to reality? The second way of comparing the veracity of the model is a contextual model evaluation, meaning, what are other studies with similar efforts saying? How close are you to other literature outcomes? And generally, there's user bias because authors choose to cite studies that they read, or authors choose to cite outcomes similar in scope. And really, it's a very narrow set of studies that you would correlate with. How about the entire landscape, right? There's all these efforts by all these groups in the US, in Europe, in India, and everywhere else. How do you compare with this bigger landscape of CTM outcomes? And that's really what my student Rishi Chandelier and I have been working with recently, is overcoming challenge number 2. Okay, so in the US, US EPA has some say in putting together model, regulatory guidelines for model performance. Under what context can you use a model, and how do you use it, and then what are the limitations and caveats? And a series of studies had come up through the 90s, 2000s, and they have been replicated in similar frameworks, for example, most recently in China, where they compare what I call this big basket of apps. So your apple, which is basically your prediction, along with other predictions, the bigger basket of predictions available from literature. What US EPA and all the related authors have said is, you could statistically evaluate all CTM outcomes, the chemical transport model predictions, as one giant basket of apples. You could see the distribution of the veracity of those predictions and see what range of correlations and associations are occurring in there. What they said is, there are 2 types of model performance that could be achieved. One is the goal model performance, the top 1/3 of CTM outcomes, meaning the best performing CTM predictions with reality. Those are called goal. You then want to relax the standard a little bit, and they said, okay, let's look at the 67th percentile, so the top 2/3 of the model outcomes, and choose that as the criteria, meaning these are model predictions you should get under a typical setting. It's not great, but it's not bad. The goal setting is something which is very, very good, meaning these are the highest kind of CTM prediction qualities that you could get. Criteria is not great, but not bad, and that most CTM studies done in the future should meet at least the goal, if not the criteria settings. So in this way, you could now compare your basket of apples, your statistical comparisons, with statistical comparisons from the entire landscape of the CTM studies. And that's what we replicated for India, where we basically went through every single CTM study published, irrespective of model name, irrespective of size of domain, irrespective of, we took every possible CTM study that had reported the operational evaluation, meaning they took observations, they took predictions, and they statistically compared it. And we wanted to see how uniform our CTM community has been for studies in India. The answer is not very uniform. There are many, many groups, actually some of them are right here on the dais as well as in the room. We all do our work, we all do it very well, but we aren't really necessarily speaking the same language in terms of comparisons. In fact, we were only able to identify about 80-odd studies from 2008 until January of 2024. And of these, only 41 studies had any statistical metrics reported for the evaluation of their CTM outcomes. A lot of CTM applications, but very few reporting very strongly the veracity of their model outcomes. In fact, I think it was 20 odd for ozone and PM 2.5. So we've mapped all the big criteria, air pollutants really, and the metrics reported, and found that there's very little consistency in how we as a community are working. And then we basically put that into a box and whisker chart, meaning we took all the biases and the correlation metrics. We looked at the normalized mean bias, R is the correlation coefficient, this is the normalized mean error, and the index of agreement. NMB and NME compare the magnitude, meaning they have similar values, they may be off. Association is do the trends compare. So R and IOA, index of agreement, are measures of association, and found that in general, we do kind of well with ozone, not so well with ammonia. We are largely underpredicting PM 2.5 in almost all PM 2.5 CTM studies for the Indian domain. Now I want to clarify, I'm not saying by Indian scientists, I'm just saying done for the domain over India. And then we kind of overpredict ozone a little bit as well. So we have a large variation in our statistical outcomes. What we did was we took all of those outcomes and rank ordered them. Small bias is really good, which means the prediction and the observation are very close to each other. Large association is very good. That means the trends are following each other as closely as possible. So we took these statistical outcomes from all of these studies, 29 for PM 2.5 and 25 for ozone, extracted the bias and the association, which is R and IOA, and rank ordered them. And then divided it into that goal and criteria. So the first 33rd percentile, the second bucket of 33rd percentile, and the last bucket, and wanted to see what our goal and criteria benchmarks look like. So those are some of our outcomes. Let me just walk you through the NMB. Close to 0 NMB is good. It means the model is performing well. 250% means it's just 2.5. So the predictions, the observations are 2.5x of the predictions in that case. At the 33rd percentile sample showed an NMB of about 17%, which means the top 1/3 studies had biases within 17%, meaning the model agreed with the observations within a 77%. The criteria was about 40%, 39, which means that the models agreed about, only had 40% of the PM 2.5 as observed, as shown by the observations. So we were able to develop the goal benchmarks and the criteria benchmarks for this landscape set of studies. And this is what we found. We compared it to the United States and we compared it to China with their latest set of benchmarks. So for the US, it was 2017, the landmark Emery et al. Paper. And China, there's a series of studies that have come out as recently as 2023, December, and 2024. So we assimilated all those values, and this is what we find. In general, our CTM studies are doing overall, irrespective of scope or time scale or spatial resolution, worse in predictions compared to the domains over US and China. And that is true irrespective of the pollutant. So be it PM 2.5 or ozone, we as a community really need to buckle down and figure out why is it that with the same level of skill, we are still getting poorer predictions for the Indian domain. It doesn't matter, across metrics, we do just as bad, compared to the others. So unfortunately, Rishi and I were hoping to kind of do a block assessment, meaning break down these numbers into where are the emissions. Okay, that's not a good surface. Sorry about that. What were the emission inputs? What were the time scales? But we had such a small sample size that we couldn't really break these numbers down any further to be able to come up with more specific benchmarks. So in general, very qualitatively, this is kind of what we found. What do we need to do as a CTM community is, and this was a big one. Out of those 40-odd studies that we were finally able to shortlist, only 10 presented their meteorological results, meaning it's assumed that meteorology predictions that are going in as an input to the air quality model is working fine, but we really don't know the model veracity of the weather predictions as well. So if weather is driving, your chemistry and your final outcomes, we don't know the veracity of those models. So very strongly presenting our meteorological predictions, because we've noticed that it is region and scale specific. Especially at about 4 kilometers, we've noticed that some of our regions which are mountainous and next to the coast can have really poor weather outcomes. And of course, we don't necessarily have the skill as many of the weather modelers, but reporting region-specific and scale-specific evaluation of meteorology is very important. The next big thing is emission inventories. There's very little consistency in how we feed emission inventories into CTMs. Take about a minute. Yeah, okay. So examples are the most recent Colliers network driven emission inventories. Having some homogenization of emission inventories would be quite helpful. For example, the National Emission Inventory Framework in the US provides a series of very standardized emission inputs to, for regulatory and other purposes. So it'd be nice to have something of that sort. Resolution matters. Scale is not always a good thing. In fact, errors go up when you go really fine. And then most importantly, for all the early career CTM people here, standardizing your metrics from the get-go, having a series of coincidence and association metrics are important. At this point, most of the CTM studies are largely WRF-Chem, which is an online model. But of course, there are many other models such as CAMX, CMAC, HIMAIR, which have been used, but we should be augmenting our capacity. Lastly, I just really want to leave you all with kind of this piece of information. I would really like to call on the modelers community here to say that we really need to augment our model diversity, do a systematic intercomparison in terms of the types of model chosen, the setup of those models and the scopes, to be able to then develop further more systematic benchmarks, increase the basket of apples per se. There is a provision for air information centers within NCAP. Could we use model outcomes to be sequestered there? Not everybody has to be a CTM modeler to do health and ecosystem assessments. So can we sequester our model runs in a systematic way that it is available plainly, transparently to the public to conduct further assessments? And most importantly, can we come together to develop an operational handbook, a guidance book for air quality modeling? Because there are extensive paragraphs on in the NCAP and other air quality programs on how, when, and where should we be running measurements. We do need something similar for the air quality modeling community. So with this, I know I overshot my time. Thank you again for that. I will take questions and hand it over to the next speaker. Thank you.
Next, we have Dr. Sarath Guttikunda. He's the founder of urbanemissions.info. He's also an adjunct professor at IIT Delhi. Urban Emissions is known for their ease of use to read primers on air pollution topics, resources and tools for emissions and pollution modeling in Asia, Africa, and Latin America. For open access materials, please check out urbanemissions.info.
Hi, thank you. I will shift gears a little bit, still modeling only, but one of the inputs to the model, airsheds. When we've heard the word airshed management and we have to manage our air quality at certain level. So what is this airshed? And then I'll show one quick example of how we used some of this. So when we say airshed, what are we looking for? It's basically a box. It's an imaginary box. It's beyond the political boundaries of a city or a state or the country. So you draw a box, and what do you want in these airsheds? These are the things we want to define. Okay, everything as a number. Okay? We want to know the trends, because eventually everybody wants to rank everything, right? PM2.5, SO2, emissions, sectors. We want to rank everything. So we want to know, what are these trends? Contributions of sectors. So if we are looking at a city airshed, we want to make that pie. How much of my emissions are coming from transport or industries, power plants. Anirban has presented the inventory work that CSTEP has done. So everything is a pie. So we want to know that sector contributions. And then contributions to each other. So this is again a presentation that Subbu showed earlier. Karnataka, how much of pollution is coming from Tamil Nadu, how much is Kerala, how much is Andhra Pradesh. We want to promote that blame game. So we want to know the contributions of like what is my neighbor contributing, okay? In general, regional coordination. So this is the application part. Now you do all these numbers in 1, 2, and 3, then we want to know, okay, now for Karnataka, 20% is coming from Tamil Nadu, so let's talk to Tamil Nadu and say, how much can you reduce, how much can I reduce? No, you have some regional coordination going on. So it's not about just the states talking to each other, then you can also do the same thing at a subcontinent level, right? India, Bangladesh, Pakistan, Afghanistan, everybody can talk to each other. That kind of long-term engagement has to come in. So when we talk about airsheds, basically we're talking about that. If you're talking about urban scale airsheds, we are talking about trying to understand the immediate neighbors. We're talking about regional airsheds, we're talking about state level or country level. Okay? Same 1, 2, and 3. So if we have to put those numbers together, this is a summary from Randall Martin's group, some of the numbers. So UP has always been 1 or 2, 3, is always there. And how much of the pollution is within UP, what are the sectors contributing to, and spatially, how does that look like? Yeah? This is just a summary. So very similar to exactly what Subbu has showed. This is for UP. So we want to know these 1, 2, and 3. What are those trends? What are the contributions? And then what can we do about it? And then this is the math part. So this is the CTM, what Srinidhi was talking about. When we want to do this chemical transport modeling, we want to do the work at urban level or regional level. Look, how do we define these boxes? So this is where things get slightly little complicated. Right? It's a mix of how much information you have to run those models and what is your target, what is your goal, what is your criteria. So all these things definitely come into picture. So when we're talking about urban airsheds, at least in case of India, in PM 2.5 and PM 10, these are our heterogeneous pollutants, and we want to basically focus on that. So when we are talking about urban airsheds, pretty much entire discussion is driven to decide what are the contributors to PM 2.5, what are the trends in PM 2.5 emissions. So in CTM, you will get the combination of everything, like primary emissions, secondary emissions, all those things are going in, but your criteria pollutant is pretty much PM. But from a regional perspective, there you can't just talk about PM 2.5, okay? So at a regional level, it's a multi-pollutant game. Okay, you have regional pollutants. CO is very uniform across the region. Now you have blocks, so you have blocks of it. With PM 2.5, you have hotspots. Now what Anirban was showing earlier in the map, you have hotspots of heavy PM emissions in one block. But then you have CO, very uniform. Ozone, very uniform. SO2, again, it's a regional pollutant. So even though it's a highlighted pollutant at large industries or power plants, iron and steel industries, but it's a regional pollutant. It contributes a lot in the long range transport. Now you need some retention time in your model to convert that SO2 into sulfates, and that sulfates goes into PM 2.5. Okay, so that's what we're going to target. So when we're talking about urban, you have a certain criteria in mind. When you're doing regional, you have a certain criteria in mind. So at the urban scale, as I said, it's a purely mathematical thing. How much can you model? Okay, and the region that you are modeling, that decides how big that airshed is going to be. So in case of Delhi, I can't draw a box very close to the administrative boundary of Delhi. It will not give me an immediate good answer when I'm doing that modeling, because it's embedded in a heavy activity region. So that airshed automatically becomes much bigger. Like how much and how you want to handle that, again, it's a mathematical thing. You decide depending on your computational power. But if you go to Indore, you have, again, a lot of hotspots. But technically speaking, you can't differentiate between Indore, Dewas, and Ujjain. They are literally 20 kilometers away from each other, and there is a heavy traffic that connects them all every day, with the freight, passenger transport, everything. So you decide, you want to do just Indore, you can do the just Indore, because within the immediate vicinity of 5 to 10 kilometers, there's not much of activity going on, so you can draw a box. But if you want to be really correct in a sub-regional level, you need to draw that box. So you decide. So you can have a full city as one box and have a very heavy computational load that you want to take on. sure, or you can have nesting also, okay? So these are things, once you start getting into the nitty-gritties of how do I implement this CTM for my modeling purposes, you will get into it. So it's a learning process. It's not something that you're going to get from the first day. So we have done, at least for the urban scale, we've defined some of these air sheds that we think are suitable for some of the CTM works. And we use it ourselves, but they're also open for works as well. Now, let's go a little bit higher. At the India scale, again, the question remains the same. What is in that box? So within the India box, how much of the pollution is coming from our neighbors? And within India states, they also have the same discussion. I want to know what my neighbors are contributing. Then the mathematical argument continues, but you can also start drawing some air sheds. Okay? These are not boxes anymore. So, but you can't be straight lines either. Mainly because you don't want to have too many players, then it becomes too much to coordinate. So then you want to limit it. So how do you make those limitations? So you can go by states, but then you have 28 states and 8 union territories, 36 people to coordinate. Okay? It's a big number. Load dispatch centers. The electrical department does a very good job. So they have 5 load dispatch centers across the country, but 5 is too small. I mean, we are very big, regionally we are very big and we have a lot of variations. That looks like too small. Meteorology. When you have subdivisions, but there are 36 subdivisions. Okay? They are very nice. It is very useful. Those are drawn with a certain meteorological features in mind and excellent. They work really well for meteorological purposes. But for air pollution, no, it becomes a little bit tedious to work with 36. But meteorology, again, also have sub-regional offices, 6 of them. Very nice, but too small. So the 5th one is what we are looking at, what we are doing in our modeling work is these agroclimatic zones. Again, these are officially designated zones, 15 of them, and they work really well. They have the same meteorological features, and if you start digging a little bit into what are the emission characteristics and what are the contributions coming from in different sectors, there's also a very nice story that one could go with. Again, the summary is from the global chemical transport model from Randall's group again. So we're basically trying to see, are there synergies that can be immediately utilized and use these 15 groups, not states, 15 groups for regional coordination. Okay? So very immediately for that, sorry. Oh, it moved. So 13 and 14, it's a very easy ones. You have the East Coast and the West Coast. So you can immediately see that the percentage contributions coming from all the different sectors are very, very uniform. Then if you go to 11, that is the arid region, desert. So you have a big chunk of dust dust shows up right away, wind-blown dust. Those characteristics are very high. So like this, for each of these, if you go to Central Plateau, 9, the Korba region, Chhattisgarh area, so you have close to 30 gigawatts of electricity generation. So if you look at number 9, the power plants, the black is like really, really high. That's high because the component of the emissions coming from power and industries is very, very high. We already know that. Okay? So generally speaking, a segregation like this can help us do a regional coordination a bit more easy. A decent number to handle, 15 air sheds. Of these, you can actually neglect now 1, 2, and 3. I'm not saying that okay, they don't need any work. They also need work, but the magnitude-wise, absolute numbers-wise, those regions are a little bit less. Now, if you want to cut down the work, but technically speaking, yeah, 15 is a really good number to work with as compared to 5 or 36. If you look at, so this is a quick application of those airshed numbers. In 1998, there were 4 of these regions which were exceeding the national ambient standard, but in 2022, 8 of those have started to exceed those national ambient standards, which basically says that we are really going up and up. Now, we tried to see the trends a little bit more deeper. Same segregations, looking at the measured PM 2.5 reported, PM 2.5 and PM 10, and some reanalyzed numbers for the NCAP period, 2019 to 2023. There is a drop, and a lot of groups are already showing these numbers, saying that there is a drop in PM 2.5, and both in the measurements that are coming in from the city and also in the model fields as well. So we are not refuting any of that. Now, I want you to take a closer look at this. So when we are looking at the air quality bulletins that are coming out every day at 4 p.m. from the Central Pollution Control Board, one of the columns in those bulletins is conditional pollutant. Means that today I have calculated the air quality index for the 5 pollutants, and the conditional pollutant is PM 2.5 or PM 10, SO2, NO2, ozone. All of them show up at some point or the other, but I want you to look at these percentages. The number of days PM 2.5 has started to show up as the conditional pollutant has almost doubled in the last 3-4 years. And it has, that's our conclusion is that it's because of the line in the NCAP saying that we have to control PM 10. Okay? And at the same time, same cities are reporting that our PM 10 numbers are going down. If PM 10 numbers are going down, why is it still reported as the conditional pollutant? So this is happening because they are putting too much emphasis on PM 10. They are measuring other pollutants, but only reporting PM 10 to the bulletin work, and it's basically showing up as the only conditional pollutant. And when we have a couple of more synthesis work on this. So AOD, for example, it's going down because it is looking at everything, right? It's not looking at PM 10 or PM 2.5, it's looking at everything. And it is going down. The column numbers over these cities are decreasing a little bit, and we're seeing that. But if you look at TROPOME, air quality, the UVAI, that's aerosol index residual, okay? And it's becoming actually more and more positive. So when the residual index is more and more positive, it's mostly because you're loading from smoke, and both organic, black and organic carbon is actually increasing. Okay? So which means that you are controlling your dust, but your BC and OC are actually increasing. So we looked at the gases from the same TROPOME fields for the same airsheds averages. You look, NO2 is increasing, SO2 is increasing, formaldehyde is increasing. So one of the conclusions that we came up with is, yes, pollution, PM 2.5 or PM 10 numbers are going down in the cities, but once you get out of the cities, it's not the same. I think this is something that, Josh and Kalpana were saying that in the morning. And anthropogenic emissions, not decreasing. Okay? So when the anthropogenic emissions are not decreasing, you have the SO2 is increasing, NO2 is increasing. Now if you look at the fossil fuel combustion rates, those are not going down. Number of cars are going up, petrol, diesel, CNG consumption is going up, coal consumption has gone up, petcoke consumption has gone up, everything is going up. Your PM 10 numbers are going down because we are putting too much emphasis on dust management in the cities and not on the management of fossil fuels. Okay? So this is a contention that we have with the NCAP groups now, saying that we have to change that language. Okay? We have to start talking about air pollution. I think here, modeling really can help in showing that. If we can build the emissions baseline, not just monitoring baseline, then we can make this story much stronger. So this is where the modeling community can definitely come in and make that case. Thank you.
Thank you for the wonderful talk. Next, we'll have Dr. Piyush Bharadwaj. Dr. Piyush Bharadwaj, my boss, heads the Atmospheric Composition Modeling Group at CSTEP. He holds a PhD in Atmospheric Sciences from Aries Nainital. Prior to joining CSTEP, he was a postdoc at Research Applications Laboratory, National Center for Atmospheric Research, NCAR, Boulder, USA. Before that, he was in South Korea, and he had a small stint at his PhD institution. His areas of interest include atmospheric chemistry, transport, and weather prediction modeling, satellite retrieved and ground-based measurements of SLCPs, and long-range transport of pollution. Over to you, Dr. Piyush.
Thank you very much, Kaushik, for that nice introduction. So the picture here shows it's not interstate transport, but it's like an intercontinental transport of different type of aerosols. So different color basically represent different type of aerosols. For example, the yellow in this image represents Saharan dust, and you have other colors. For example, the blue one is sea salt. So in this talk, I'll try to quantify the interstate contributions of different Indian states. So this is an ongoing work. So in this study, so one thing, I think Srinidhi has already introduced what CTMs are, but I'll still just go through it. So pollutants basically gets emitted into atmosphere through different processes, and then they undergo transformations. They are transported to different regions, and eventually they get deposited by wet or dry deposition. So this is what I call is a fate of air pollution. Some of the emissions are primary emissions, for example, black carbon when you burn something, and then some of the species are formed in the atmosphere through other emission sources like ozone. So you emit precursors like NO2, volatile organic compounds, and you form ozone in atmosphere. So another question which is very important when we talk about air quality management over a region or over a city is that what contributes to pollutant concentration over a region of interest. So of course, you have emission of pollutants and precursors from that region. And there's one more important fact that air pollution doesn't stay at a place, it moves. So if you combine these two facts, so air quality over a region is a combination of local and upwind emission sources. So if you want to have a local level interventions to reduce pollutant concentration, it may or may not be very effective in reducing, in improving the air quality of that region. So in summary, it is very important to calculate that how much of the pollution is coming from the outside of region of interest. And I was very glad that yesterday when I saw the Kalyan Rudra's presentation that there is some, in PCBs, people are aware that there is actually a lot of contribution from outside which they cannot control. So it is very important to include that in whatever calculations you want to do. So our model of choice, we have used weather research and forecasting model for weather inputs, weather outputs. So this model basically simulates met parameters such as temperature, winds, and humidity, etc. And the weather output, along with emissions and boundary conditions from other model, is used in a chemical transport model called CAMEX. This CAMEX model basically simulates the time evolution of pollutant concentration of gas and aerosol species. There is one utility in CAMEX, which is called PSAT, Particle Source Apportionment Tool, basically which you can use to tag emission from a certain region, and you can basically quantify the interstate contributions. So our study domain is basically entire India. So this plot here shows the terrain height of our model domain, and CAMEX is run over different configurations. For example, the MET, the model for meteorology is this domain, but we have run CAMEX at different places. One of the region is southern India, so I will discuss the results for this simulation. So these are the inputs emission that we have used for our modeling setup. So this is PM 2.5. So these are the 5 southern Indian states. The total load is like this much. For example, if you see here, Kerala, it has very less total PM 2.5 emission, and the large share of that is from residential sector. So these type of details are very important when you want to have interventions. This is SO2, this is NOx. So these two are precursors for PM 2.5. The different color in these bar are different states, and then different colors in these pies are different sectors. So this is how output from a typical global emission inventory looks. We also used, apart from these anthropogenic sources, we also used other emissions like biogenic emissions, fire emissions, emissions from oceanic sources. So this will give you an idea that how the movement of fine PM happens across southern India. So in this case, the source, we have only considered sources from the Karnataka state. So you can see that this transport changes direction with respect to seasons. So this is, winter is basically December, January, February. This is March, April, May. So in different seasons, you can see this this is a daily average plot, so you can see how the plumes are moving. On the flip side, so basically the point here is that Karnataka, the emission sources located in Karnataka can pollute other states and other regions. And on the flip side, Karnataka also receives a lot of contribution from other states. So this is the emission from all other southern Indian states, and this is how they this is how Karnataka is impacted by the emission from other regions. So in one of the plots, Karnataka is a source, in other plots, it's a receptor. So it's very important to know the fact that this state could be a source or a receptor depending upon the season. So this is, so in this slide, we are trying to quantify what is the seasonal contribution of PM 2.5 from different states. So the black color basically shows the local contribution here. And this darker gray color shows the contribution of other southern Indian states. And the light gray color shows the outside contribution. This outside includes other states in India, and it also includes sources located outside of India. So if you can, there are a few interesting observations here. This is the local contribution. So for example, if you see Andhra Pradesh, the local sources only contribute to 29 to 42% of its air pollution. So if you want to put a local intervention, you want to target local emission sources, then you won't be getting a lot of benefits in terms of air quality improvement. While states like Tamil Nadu, you have much higher, this number is relatively higher, it's 50 to 70%. And you can see that in certain season, it goes very high, so it's very, so you can basically control air quality in those regions. So let's add some color to these plots. So now the black is basically, for each state you have a different color. For example, Andhra Pradesh is red, and this is the contribution from other states. We can also keep going in this way and also decouple this information, but it's not important for this time. So probably you get the idea that how each state is contributing to different state. So this is again the same plot, but I'm showing the spatial distribution. So this is basically the local contribution. And you can see interesting pattern here that as you move towards south, the local contribution to PM 2.5 levels, it increases. So for certain states, it's very important if they target the pollution sources located inside that, while for other states, they probably need a regional coordination to improve air quality. Okay, there's some lag. So this is again the contribution, the same thing which I've showed. This is the spatial distribution. So here you can see the Karnataka's contribution was about, I think, 25 to, no, it's about 40%. And from southern Indian states, you can see the largest contributor to Karnataka's PM 2.5 is Andhra Pradesh. So if maybe Karnataka, Andhra Pradesh and Tamil Nadu can talk to each other, they can improve the air quality over Karnataka. And as you go south, if you see states like Kerala, most of the air quality is controlled by the sources located inside the state. This is one more layer of information. So this is basically the sectoral information as well. Here you can see the which sector is dominant. So for example, residential sector is very important for states like Kerala, where it is about 43%. But for states like Karnataka, there are 3 different sectors that contributes almost equally. So Sarath was talking about, okay. Just a minute. Sarath was talking about air sheds. So in CAMX, what you can do, you can define source and receptors. So in this case, the results which I've showed, these all are the source regions, and receptor could be anything. So in this plot, what I've tried to do, I tried to calculate the contribution of PM 2.5 from each of these states to the Bangalore urban region. And you can see that this is the contribution of the home state, Karnataka, and it varies a lot with respect to seasons. Now we wanted to know further that, it is quite obvious, right, that the cities or the districts located nearby Bangalore would be the most interesting ones. So this is extra layer of information. If you consider those districts, you see that half, this is the annual scale. So half of that Karnataka's contribution is basically coming from these 2 regions only. So if you want to control PM 2.5, just focus on these 2 districts. You need not to focus on entire state. So this will give you some idea that you can, it's like a multi-jurisdiction approach. This is also like an airshed, but for a smaller region. And so here you can see that 5 neighborhood districts surrounding Bangalore contributes as much as rest of the Karnataka. So if your actions are in this part, it will be very effective. One district, this is called Krishnagiri, in entire state of Tamil Nadu, it contributes to about 1/3 of the PM 2.5 pollution coming from Tamil Nadu. So if the Tamil Nadu government, for example, agrees to control emissions from this region, it will also, the Bangalore will also benefit from the, in terms of air quality. So we need provisions like good neighbor, which is there in US under the Clean Air Act. But why do you believe my numbers? Because Srinidhi mentioned, right, that we should have model validation. So we did evaluated meteorological variables as well as chemical variables. So the top figure is the 2-meter temperature, and the bottom, so the green, this color, the blue color here is your observations, and the orange color here is your, blue is your observations, and the orange is your METAR, so METAR data. METAR is basically meteorological data from airports, all the airports. And you can see here that in 2-meter temperature, we are overall getting an underestimation with the exception of monsoon month. And these are the numbers. So the black color basically is showing the mean bias, and these are the normalized mean bias in this season. So you can see that there is a overall model overestimation of about 10%. But why 2-meter temperature is important? Because it affects the height of planetary boundary layer and the pollutant mixing. So this is why. And we also evaluated 10-meter wind speed. So here we can see that overall model wind speeds are slightly higher as compared to observations. And this is quite a known phenomenon because model is unable to capture subgrid scale topographical features. So you can have higher wind speeds. And PBL schemes in WRF also tend to over-predict low and moderate wind speed. So in observations, you have a lot of calm winds, a feature called calm winds. In model, you don't have those calm winds. So your model wind speeds are higher. But why do this bias in wind speed is important? Because that will tell you whether how fast the pollutant can travel from one region to another. So we also compared our PM 2.5 output from our model from a satellite. This is Van Donlekar et al. We have taken data from this satellite-derived product. And the dots here is basically the CPCB CA QMS sites. So this scatter plot is from the CPCB sites and the CAMX model output extracted from those locations. You can see the agreement is overall good. Mean normalized bias is 17%. So Srinidhi was mentioning that if it is less than 17% for India, it's good. So these results are good. And R value is around 0.51. And this is for 2019. So the preliminary takeaways from this study is that while considering multi-jurisdictional airshed approach, we should consider the seasonal patterns in winds, and one region could be source in one season, it could be receptor in other season. And focusing on select area sectors based on this would reap maximum benefits in terms of air quality improvements. And these are the things which I discussed earlier, that for example, states like Karnataka and Andhra Pradesh requires a coordinated effort among southern Indian states if they want to improve their air quality. And the states like Tamil Nadu and Kerala basically can have because they have a lot of contribution from the local emission sources, so which indicate the high confidence in reaping benefits from local clean air action plans. So detailed sector analysis is under progress and will soon release our results. Thank you very much.
Yeah, you can go. Thank you so much, Dr. Piyush. Next, we'll have the questions towards the end of the session. Next, we have Dr. Sachin Gude. He's a scientist at the Indian Institute of Tropical Meteorology, Pune. Additionally, he serves as an adjunct professor at the Department of Environmental Sciences, Pune University. His work spans across atmospheric chemistry, urban air quality modeling, fog modeling, chemical data assimilation. He leads the winter fog experiment, WIFEX, in India, and heads a research group dedicated to atmospheric chemistry and modeling. Over to you, Dr. Gude.
Good afternoon, everyone. I would like to thank CSTEP for giving this opportunity to talk about what IITM is doing in terms of air quality modeling to support the proactive mitigation strategies, measures in various districts of India. IITM basically do a basic research in air quality, process level chemistry or modeling. But since it is a ministry and sometimes we get requests from other ministry to develop a support system for them, and obviously we have to develop such system. So development of this air quality early warning and decision system, support system was directly came from PMO in 2018 when we had this dust storm and a lot of people died. So they wanted us to develop a early warning system that will support the decision making activity in larger region of Delhi NCR. So I'll mostly talk about the air quality warning and integrated decision support system for emissions, which we have recently developed. And this system is now being used by Commission for Air Quality Management to understand the air shell in Delhi and surrounding districts, to manage the air quality and to activate the various graded response action plan to control the short-term air quality in Delhi and NCR. So coming to the modeling, so this is basically a very complicated system, and we have taken almost 5 years to develop this system. This is an advanced air quality modeling system integrated with different kind of components. The heart of this system is basically online air quality model. When I talk about online, because aerosol and radiation feedbacks, they play a lot of role during winter time, and we need a model which will actually give those effects to simulate the air quality or PM 2.5 concentration in Delhi. So we run this air quality model in a dynamical downscaling fashion at various resolution, but give the forecast, final forecast at 400 meter resolution for entire Delhi NCR. This model is also coupled with certain different components. Some of these components are basically to enhance the accuracy of the air quality forecast, and other components are basically meant for the decision making activity. For example, this chemical data assimilation, we are doing a lot of chemical data assimilation, because once you run the air quality model, they obviously deviate due to the nonlinear interaction between various chemical processes, metrology, and you need to correct that model time to time. So how we can do that? We can do with the chemical data assimilation. So we do a lot of data assimilation. We take satellite data, we take ground observation, whatever data is available in terms of chemistry, we assimilate all those data into the model. Also, model deviates or model gives error if the weather is incorrect. So we need to have a proper weather also in the model, and to have a correct weather, we also do the lot of weather data assimilation, so that time to time weather is not deviating from the reality. So we take all the observations from the IMD network, be it AWS, whether it is a radius one day observations, and we assimilate that data to correct the model weather when we deliver the forecast. Fire data assimilation is also important when we try to simulate the air quality in Delhi. We do fire data assimilation, and now this model is implemented with the passive tracer. So they track the different sources, different sectors, and give you information about what is contributing to the air quality at each and every grid of 2 kilometer resolution. So you get information about what sectors and what sources are contributing to the air quality in that particular grid, and in what way you can control the air quality, what are the sectors that should be targeted to manage the air quality in Delhi. And this system also have a built-in air emission scenario. So you can implement a different air emission scenario and see how much air quality will exceed the levels or will control the level. So that kind of scenario is also built in this system. And finally, we also do day-to-day verification to see that whether the air quality model is deviating from the reality, or we need to do more efforts on improving the air quality forecast. So this is entire system. It took almost 5 years to build that system. And if you look at how this system is running now for Delhi NCR, so this is a day-to-day variation. If you look at the plot at right side, so it is a 5 years of day-to-day variation. So every blue block is a 5 years of PM 2.5 variability on that day, and every red block is basically observed variability on that day. And you can see that the model is doing pretty good job in capturing the levels what we see in Delhi. So capturing the levels of 300, 400 and 500 microgram using a chemical transport model requires a lot of fine tuning and improvement in the model. So overall you can see that the model is pretty good in capturing the air quality levels in Delhi. In terms of air quality index, if you look at the very unhealthy air quality levels or unhealthy air quality levels, model is pretty good. If you look at probability of detection and the success ratio in capturing the air quality falling in that criteria, it's close to 100. So basically we are able to capture each and every air quality days which falls into that criteria. But still model is not doing good for the critical levels of air quality. For critical levels of air quality, when air quality goes beyond 400 AQI, model has a limited success. The success is somewhere around 65%. And why this is happening? Most of the time, the model is not able to capture those levels when biomass burning season is active. And there are a lot of uncertainties in the biomass burning season. You cannot predict how much fires will occur next day or day after. And this is a highly certain area. So that's why you get little uncertainty when the biomass season is active. And another uncertainty is introduced when you have a dense fog in Delhi. So dense fog involves a lot of chemical processes that transforms gases into aerosol, lot of secondary aerosol formation occurs, and that is not good, still good in the model, and therefore we miss the air quality events that is falling beyond 400 AQI category. But overall, the model is very good if you want to use this model for management of air quality, and this has been adopted by Commission of Air Quality Management. Sorry. Oh, please. Okay. Yeah. So since we developed this model for commission, but then later on many state agencies, they also required similar kind of system, and we have been extending this system for Mumbai, and hopefully this will be operational in this season. Then we have also implemented this model for Jaipur, and will be implementing for air quality management, district-wise air quality management for a larger region of UP. But what is coming from this system? If you look at the 5 years of air quality distribution in Delhi, particularly during winter months and the season when biomass burning is active, so Delhi has a dynamical air shade, and you cannot target the actions only focused to Delhi, and it has a 3-leg structure. So if you look at the distribution, 30% of contribution to the air qualities in Delhi is coming from the sources within Delhi. Rest of the 30% is coming from districts surrounding Delhi, that is 24 districts, somewhere around 24 districts. But around 35% of contribution is coming out of the NCR region. So it is a larger Indo-Gangetic region. And if you really want to implement some strategies to control air pollution in Delhi, you need to have an implementation plan that is not only focused in Delhi or NCR district, but there should be some implementation plan required for larger IGP basin. If you look at biomass burning, so during biomass burning season, you get a contribution somewhere around 10% in mean during October and November, but on a day-to-day basis, that contribution goes up to 30%. And for different AQI categories like 0 to 300 or 300 to 1400, so pretty much the distribution is same. Even if it is a 300 AQI, even if it is a 400 AQI, or it is a 500 AQI, the contribution is a still 3-leg structure. So you need to have a management plan not only focused on Delhi, but for entire IGP basin. Yeah. And another problem that requires attention and that is creating mess is a strong aerosol radiative feedback. If you look at the vertical distribution of aerosol, this is a aerosol backscatter during a peak biomass burning season, and you can see that it is not, the aerosol pollution is not confined to the surface. It is distributed throughout a 1 kilometer of boundary layer. And because of this thick layer of aerosol, you get lot of aerosol radiative feedbacks, and that adds to the already poor air quality in Delhi. And what we have seen basically is that if the radioactive aerosol feedbacks are active, you get additional pollution enhancement of around 100 microgram per meter cube. And you can see that it reduces the boundary layer height, it enhances the PM2.5 concentration at the surface, and that contributes 92% increase into severe air quality. Only aerosol, meteorological feedback, it has nothing to do with the sectoral contribution. So meteorology, aerosol radiation does play a lot of role in aggravating the aerosol pollution in Delhi NCR districts. And it is a positive feedback loop. If you try to reduce the emissions from Delhi NCR region, obviously its impacts will get reduced down. And so in a non-linear fashion, you will get much more improvement in air quality in Delhi. Yeah, one of the objective of air quality early warning system is to implement a graded response action plan. So what Commission for Air Quality does, they take the forecast from our system, and 3 days prior, if we predict that the air quality is crossing certain AQI level, then they implement a graded response action plan depending upon the air quality prediction. Now, if air quality is crossing the 200 AQI, then they turn on the graded response action plan, the GRAP 1. If it is crossing certain level, then they turn on the GRAP 2. So these are the restrictions based on the air quality forecast. And if you look at the kind of restriction that were imposed during 2023 and 2024, so most of the time GRAP 1 was active throughout the season. GRAP 2 was most of the time it was again active. GRAP 3 and GRAP 4, they were activated and they were revoked depending upon the improvement in the air quality. So what is the impact of this GRAP 1, GRAP 2, GRAP 3 activation in Delhi? Whether they are really leading to the improvement in the air quality, short-term air quality in Delhi. So we did some sensitivity simulation based on GRAP activation. So bottom figure shows the days when the GRAP was activated and the period for which the different GRAPs were activated, and top figure shows the AQI in different category. Okay. So you can see that whenever GRAP 3 and GRAP 4 is activated, you get lot of improvement in the PM2.5 pollution. So whenever the restrictions are imposed in Delhi NCR, you get an order of 50 to 100 microgram of control of air PM2.5 particulate concentration in Delhi. So they are effective. GRAP 3 and GRAP 3 are actually effective. They can control air quality levels at certain level. And if you look at the AQI, sorry. Yeah, yeah. So you get a change in AQI unit of 100 maximum up to 100, but in the mean it is a 40 to 60. So 40 to 60 is very good change in the AQI. They actually change the severe from severe air quality to poor air quality kind of regime. So GRAPs are actually effective for controlling the short-term air quality in Delhi NCR region. I'll skip this slide. This is again how much health benefits we are getting from the activation of different kinds of GRAP. If you look at in 2023, so because of activation of different kinds of GRAP, we could save around 177 mortalities in Delhi. So that death we could avoid it. Even in winter 2023, when air quality was more severe compared to 2022, so you get more benefits in 2023 and 2024. Yeah, coming to policy, so we really want to see whether because Delhi was the center of the controversy, and since long there has been different policies which were implemented, which were framed and enforced in Delhi to control air quality, not only in Delhi for NCR region, and there are some Delhi-centric policies, there are some national policies, whether those policies are giving any benefits, whether those policies are really penetrating into the Delhi's air quality. So we have a long-term record of PM2.5 measurement in Delhi since 2010 till now. And when we looked into the trends in PM2.5 and PM10, you do see a lot of changes in PM2. So PM2.5 and PM10 levels are changing, are reducing, and the trend is more pronounced during winter and post-monsoon period. So if you look at the different categories of AQI, so poor days are also decreasing, very poor days are also decreasing, and severe days are also decreasing in Delhi. So policies are really getting penetrated into Delhi and NCR, and we are getting benefits of that improvement. Although the level are still much higher, what about the biomass burning policies? There are, just 1 minute. So there are lot of restrictions now and lot of policy enforcement is occurring in the state of Punjab and Haryana to control the biomass burning. And if you look at the burnt area, because fire count is not good, it is decisive, but if you look at the burnt area, you do see a lot of decreasing trend in the burnt area product. So the policies are also working for controlling the stubble burning in the states of Punjab and Haryana. I'll skip this slide. And last point I would like to add, because there are many suggestions are coming whether we should control the air quality by installing smoke towers or cloud seedings or sprinkling, but these are not effective. If you look at the pollution in any region, it is a thick layer, and by sprinkling the water or just putting the smoke guns, you will not able to control air quality in Delhi. Like for example, this smoke gun, it says that it will clear the around 1,000 meter cube of air per second, but if you calculate how many days it will take to clear the air of 1 kilometer of height, it will take 35 days to clean only 1 kilometer of cube. So those solutions are not effective, and for that we have initiated new modeling technique using fast AD simulation. Hopefully in next conference I will able to show what are the results. Thank you so much.
Thank you so much, Dr. Gude. Next, we have Professor Daniel M. Westervelt. He's an associate professor at Columbia University. He's also a faculty member at the Data Science Institute at Columbia, a scientist at NASA's Goddard Institute for Space Studies. His current research spans from air quality and climate modeling to deployment of low-cost sensors. He will present on policy-relevant insights at the nexus of climate and air quality modeling.
All right, so I'm going to talk about a slightly different class of models for the next 12 minutes that really allow you to get at the emphasis on the two-way interactions between climate and air quality. So first, just a little bit of discussion on the different types of air quality and climate models. A lot of this has already been said. But we have what I would kind of consider more of the pure air quality models, things like CAMX, which I think Piyush presented really nicely, CMAC, which is used in the United States. These are typically higher resolution models that include a lot of advanced chemistry, a lot of really nice emissions inventories. These are really good models for air quality. And then we have sort of models that can do a little bit of both, things like WRF-Chem, GEOS-Chem, Musica, which comes out of US NCAR. These also typically have pretty detailed chemistry and some climate applicability, but often are unable to diagnose responses in things like temperature and precipitation based on changes in aerosols. And then we have sort of the pure climate models. These are kind of the IPCC or CMIP class models that I think people are probably familiar with. There are, I think, 50 to 100 different models out there now in CMIP, some of them listed here. These were really designed to be climate models, but they still get used for air quality. The air quality the chemistry is pretty simple. The emissions inventories are pretty basic, but there still is some merit in using them for air quality, especially if you want to know sort of the two-way interactions between how climate affects air quality and how air quality results in changes in temperature, precipitation, and other climate variables. So why can't we do all of these things in one type of model? The short answer to that is computational power. So all of these models, when you're solving hundreds of differential equations over and over again in different little boxes, that takes time. Even the fastest supercomputers in the world, you're going to have to make some trade-offs. Do you want higher resolution? Do you want a full isoprene chemical mechanism with 500 reactions? or what basically do you want to do? So I think a version of this figure was shown very nicely already a couple times, but most of these atmospheric models have this common framework where there's a discretized box set up in the atmosphere. This can be sort of regional with boundary conditions, or it can be global. The resolutions vary quite a bit if it's a regional model versus a global model. The meteorology or the weather is usually either directly simulated from first principles or used as sort of input from reanalysis. And then you have, of course, all the typical things that I think Srini mentioned really well in her talk about the chemical solvers, advection, deposition, and so on. So this quote was brought up before: all models are wrong, some are useful. This is a figure, or a series of figures from a paper that we did a few years back with Dr. Chandra from IIT Bombay. And what it's showing is the PM 2.5, so these line graphs at the top are showing the PM 2.5 as simulated by the CESM2 model versus observations in India. So a few different cities in India. And the CESM2 model is probably one of the most widely used climate models in the world. And you can see that even though it is so widely used, there's some really big discrepancies with the air quality simulation. The trends sometimes are, getting right in terms of the seasonality, but sort of the magnitude is often quite far off. And so one of the take-home points that I like to think of from stuff like this is it's often not the best idea to just rely on a single model, especially if you're going to be thinking about policy applications. Multi-model studies are really valuable because they kind of take the bad parts of a lot of different models, the good parts of a lot of different models, and kind of mold them all together in one big ensemble, and you can really, hopefully get a more robust decision-making out of that. So these, climate models can, diagnose the impacts of emissions policies on things like air quality and climate. Like I said earlier, they're most traditionally designed to be used for climate, but we can also use them for air quality. Common, air pollutants mostly exert a net cooling on the climate, if we get into that. So this is especially true for scattering or reflecting aerosols, things like sulfate, nitrate, certain organics. These will basically block or scatter incoming solar radiation and exert a cooling impact on the surface. But it's hard to really give a one-size-fits-all answer for that because it's really, it's composition dependent. Black carbon, of course, we've been talking about that a lot. That's also part of PM 2.5. It's an aerosol. It is a warming agent. So it absorbs heat, it absorbs sunlight, and basically gives you kind of a warming effect as opposite to the scattering aerosols. But there's really a lot of uncertainties in this. And this figure here is from one of the IPCC reports. And you can see that what it's showing is the radiative forcing from these various particles composition. And if the radiative forcing is negative, that's a cooling. If it's positive, that's a warming. You can see that overall aerosols are a cooling, but the error bars are really huge. All right, there's a large range of how much cooling or how much warming there might be. So it's really crucial in light of this to seek policies that are kind of win-win for both air quality and climate. And across the board, air pollution reductions policy will have major public health benefits, but major climate disbenefits. And an example from a climate model from a series of papers that I did over 10 years ago or so, we did a study where we imagined that hypothetically you could reduce air pollution levels to their 2005 levels. And this was just the anthropogenic air pollutions, not including CO2 and methane. So just kind of like your criteria pollutants, your PMs. Removing those overall, on average, caused a significant amount of warming, all right? And that's because since the aerosols are mostly cooling in nature, you remove that cooling, that is essentially a warming. And so, our results here in this map here, this was at the global model, you can see, this is a temperature change in Celsius, degrees Celsius. You get a lot of warming. I think the average is at least a degree. And, as a planet, we've now gone past the 1.5 degree, guideline that scientists put forward. So that's kind of a moot point. But if you want to try to meet a goal of 2 degrees C or something like that, just with clean air policies, you're going to have a hard time because, you get this warming from the removal of those scattering aerosols. So it's really important to have a source-specific air pollutant reduction policy. The answer to this problem is not, let's just keep polluting more and then we'll cause less warming. We don't want to do that, obviously. We want to prioritize people's health. So you really have to emphasize the fact that we need to figure out joined-up policies that can both give you positive results for air quality and positive results for climate. So a good start with that would be reducing black carbon. Obviously a win for public health and a win for temperature, all right? You reduce black carbon, you're gonna reduce extreme warming. It turns out that it also might be a win for extreme rainfall as well. As we all know, climate is a lot more than just temperatures. Things like extreme weather, extreme storms, extreme precipitation, can cause flooding, landslides, all kinds of natural disasters. So we did a study where we looked at what would be the impact of pre-industrial versus modern day aerosols. So if we took a difference between what the black carbon was in pre-industrial times to what it is now, so obviously a huge increase in black carbon, what impact does that have on precipitation? And that's what these plots here are showing. This is the June, July, August, September average precipitation if you change one of these types of aerosols. So we did it for sulfate, black carbon and sulfate together, and then black carbon, sulfate, and organic aerosol together. And I want to focus just on the black carbon here, because that's what we're talking about right now, which is kind of panel C in the upper right. And that big increase in black carbon caused mostly an increase in precipitation. So if we flip that around on the other end, we say, okay, if we decrease black carbon, then we probably have a decrease in precipitation. So in other words, reducing black carbon may moderate extreme monsoon precipitation that can cause landslides and flooding, et cetera. And this is from a paper that I did a few years back with the citation right there. This is sort of a summary of kind of win-win policies for air quality and climate change. So this map here has kind of 2 axes, the air quality axis and the climate change axis. And we want to get towards the upper right, which is sort of the green area, which is win-win for climate and air quality. So something like sulfate reductions or SO2 reductions, clearly a win for air quality. Unfortunately, not great for climate. It's going to cause warming. And that was sort of that point I was making with that figure a couple slides ago. Let's take black carbon on the other hand, win-win. Methane reductions, also win-win. So methane is a strong climate forcer, stronger than CO2. It also is a precursor to ozone. So removing that CH4, you're going to remove a lot of that ozone. And so that's another air quality co-benefit. What about CO2 reductions? So CO2 reductions, obviously a win for climate. A little bit unclear about if it's a win for air quality. And why is that? Well, as you get warming, you often have competing and complex effects on how that warming feeds back on air quality. All right, so there's a two-way interaction here. Climate change affects air quality or air pollutants, and air pollutants affect climate change. Yeah, this was laid out in a really nice study that we've already talked about by Subbu and folks here at CSTEP, the case for action on black carbon. And this isn't necessarily that new of an idea either. This paper came back, this figure comes from a paper that's been cited, I don't know, like 15,000 times by Drew Shindell using the NASA GISS climate model. And it looks at, what are the co-benefits from mitigating black carbon and methane at the same time? All right, so, agricultural mitigations or all kinds of different technological mitigations that you can implement. And there's things here like annual premature deaths avoided. And these giant circles that you see kind of for that are, one of them is India and one of them is China. So there's other things too, like the temperature benefits, the crop production increase that you would get, crop yield, I already said premature deaths, decrease in atmospheric forcing, et cetera. So that's a nice paper. Yeah, so just to summarize, climate change impacts air pollutants also impact climate change. When you have future climate change, you get things like changes in precipitation. Precipitation is the main sink for PM 2.5. So as you change the distribution of precipitation, of rainfall, you're going to change your PM concentration. So that's a huge connection. There's also temperature dependency between climate and air pollution. There's circulation dependency, so we might have more stagnation in the future, windless conditions. There's feedbacks on the biosphere that cause wildfires. Folks in the US, we've experienced that a lot over the last 10 years, where with climate change, we're getting more wildfires, and that's really what's causing any air quality problem now at this point in the US. A lot of the anthropogenic pollution has been cleaned up, and we have a lot of wildfire problems now. Yeah, so this is a good summary figure. This figure is extremely dense. I don't expect you to kind of understand all of it, but what it does is it takes a certain physical process in the atmosphere, in the Earth system, and it tells you with climate warming in the future, what is going to be the resultant impact on particulate matter and ozone. So to give you an example, we got some trees up here. So as you have a warmer climate, that stresses out certain types of trees. They emit more BVOCs, and then that also it causes more formation of secondary organic aerosol, and then that worsens air quality. For ozone, it's a little bit unclear because there's complex nonlinear chemistry with NOx and ozone and VOCs. So yeah, I think to summarize, air quality and climate models are useful tools for policy decision making. You can ask questions, hypothetical questions, like what's the specific effect of some emissions control policy. The complex nonlinear interactions between air quality and climate means that crafting win-win policies looking at specific sources is really, really important. Avoiding, reducing sources that co-emit warming and cooling agents together, or only cooling agents. And BC and methane mitigation remains a feasible path for achieving both improvements to human health while also avoiding climate disruption. So with that, I'll stop, and thank you for listening.
Thank you so much for the talk. We'll open the floor for questions from the audience. Can raise your hands over there. Yeah, we'll go to you next.
Hi. Yeah. Hi. I'm Sarana from Bosch. My question is to Sachin regarding this graph which you have mentioned. So two questions I have. One is how long this graph will be activated, and while activating, what kind of influence it has on economy of the state?
No, which graph?
Graph. The
Graph.
control measures.
So graph will depend upon, so it's basically for the controlling of air quality, short-term air quality. So whenever you will have the air quality crossing prescribed limits, so there are compulsions to activate the graphs in winter period. So once you control the air quality, then you need not to activate the graphs. Yeah, but there are guidelines which are coming in. One is for short-term air quality, which is GRAP, and then mid-term and long-term. When this policy will penetrate into the system, then slowly you will see that the graphs will no more effective or will be implemented. It is a long-term. It requires long-term efforts. Yeah.
Okay. So what about the influence of GRAP on the economy? Like if you cut down some industrial production or reduce the transportation, for example, like.
Yeah, so that actually is not my domain to evaluate how much it will impact on economy. So Yeah, there will be definitely economic impact, but then you have health impact also. And the life of individual is more than what you lose in terms of economy. And if you look at, like, if you activate the grab, you get benefits of 80 to 100 AQI unit. And that translates into the saving of 270 to 27 lives if you calculate the short-term mortalities. I think that is a substantial benefits. Yeah.
Thanks. Can I have back here? Yeah, back here. I have a question for Sarath and Piyush. We were looking at two approaches. One is the airshed approach, and one which had a very demarcated where the states are contributing to for the air pollution. What I want to understand is, as a regulator or as a decision maker, since an airshed approach is not resonating with the jurisdiction completely because it's more of an agroclimate and the contributing factors are on that. So where does somebody take decision upon, whether it is this state-wise demarcation and you have exact controls like what's happening and you take decisions, or whether it's the airshed approach? So if you can throw some light on that.
Hi, thanks. I think it's a proposal. So like I said, we can go with the state PCBs. But what happens here is within states, we have a lot of variation in the climatic zones. And there are a lot of similarities also between the states also. Like for Deccan Plateau can be one unit. Because climatically thinking, it all moves, all the air moves in a certain way that we can simulate. Okay? So it's a proposal. So if we go by the jurisdiction saying that, okay, I don't want to create no new jurisdictions, then we go with the states. But if we want a more homogeneous management of air quality in our entire bed, then this is a good proposal to pick up on. So this is something similar happens in US and EU as well. They've gone through this, something that happened like 30, 40 years ago. But we are in the process of digesting the same methodologies.
That's a very good question. I would say that in the beginning, it's easier to control things in your own state. So in that sense, you can control sources located inside your state. So that is why I said that if your focus should be what are the most important districts that are critical to air quality over a certain region. So you can focus on that. And as Sarath mentioned, I think that is like a long-term plan. At some point, you need to realize that a certain type of geography needs to be there as one airshed. You cannot just split it just because they are two different states, because air moves. So in long term, you should have airsheds based on specific type of meteorology or the geographical region. But initially, because you do not have a framework, so you can just start with a local state and then you can move forward.
So just a quick, we see geographic boundaries very sharply, right? But there are several instances where administrative boundaries in India are kind of redrawn. Think of the census, think of NSSO, if you talk about how the public distribution system pushes down rations, basically, to rural poor versus urban poor. Those boundaries don't necessarily conform to our traditional ULB boundaries or even district or Zilla Parishad boundaries. So it's not that the Indian government does not have mechanisms really to redistribute boundaries if needed. There are multiple instances in health, in nutrition where that's happened. In fact, agroclimatically, the NSSO boundaries add up to your 15 agroclimatic zones. So it's just a matter of revisiting perhaps some of the infrastructure in delineating these geographies a little differently than the maps that we are so used to seeing on a daily basis.
Dr. Panna, yeah.
Yeah, thanks. I think an excellent session and great work by all the panelists who presented. And a very good illustration of how science is assisting, policymakers in taking decisions and what more they can do in future. But my question specifically is to Sachin. is you mentioned about your Jaipur work also. You know, Delhi, we understand that it's influenced by the fires in Punjab, Haryana, and you had that figure of 65% accuracy. But is Jaipur might not be so much sort of impacted by this. So there, does the accuracy increase during the winter time? Because GRAP is especially coming in Delhi during the winter time, and that 35% margin is a sort of on the higher side. And a follow-up question is on the emission inventory. So if I'm not wrong, probably which year emission inventory are you using, and is there a proposal to upgrade that?
Yeah, so coming to emission inventory, so we have used 2019 emission inventory, and then every year we scale it to that year. So depending upon the development that took place, like transportation sector or industrial changes, that information we get from the commission, and then accordingly we implement those things. So emission inventory we basically upgrade. So base emission inventory was 2019. Till 2023 we use that emission inventory, but this year now again there has been a new emission inventory at 500 meter resolution covering entire NCR. So that now we'll be implementing, so that we'll have most updated emission inventory. And that is very important. When you decide about the GRAP and source contribution, your emission should be updated. Coming to Jaipur, Jaipur we don't often get air quality crossing 450 or 500. So in terms of accuracy, we get mostly very poor or poor air quality levels. And if you look at the statistics, it is very good. The model is pretty good to capture day-to-day air quality falling in that area. Another problem Jaipur faces is the dust emission coming from the deserts. And model is able to capture dust, because dust is not an emission input. This is coming from the geographical feature, how much land is getting eroded because of the winds. If your winds are correct, you get pretty good dust emission.
Hey, so great presentations from all of you, and really interesting session overall. I have questions for all of you, but at least I'll start with one. So towards the end, I think Dan's talk kind of scared me a little, because he said we need to use a lot of models to actually come to the answer. It seemed that way. But, you know, I mean, just thinking about the general air quality management space in India, currently, you know, we don't even use any much air quality modeling to develop clean air action plans, right? I'm sure Sachin can talk about the sort of challenges he faced trying to push your modeling approach to inform GRAP. But, I mean, how do we actually bridge that gap? Is there a way for space for models, and this probably to Srinidhi, is there space for models to have policy relevant models to be used in place of, you know, traditional CTMs? And others can chime in as well.
See, as far as space goes, we have a lot of space to model. And I don't think we should be scared with Dan's presentation. When he is showing is what is definitely possible, and going beyond the regional influences. We were looking at global influences as well at the same time. And then, so we have feedback benefits. But we can step back and say that, okay, I mean, that's the top level that I want to reach, and I want to have all those systems running. But we can definitely have more urban and regional systems running at multiple institutions where, you know, that ensemble work can be done, and say that, okay, everybody has inventories, everybody has modeling setups, so we can have an ensemble setup where, you know, you can all like bring them all in and share the learnings. I think that's something already happens at EWS for Delhi, but more applications of that has to happen.
Right. Yeah. I was kind of hoping more for something along the lines of RCMs.
Yeah.
And that's what kind of indicated towards Srinidhi.
Yeah, so look, the idea of CTMs really is very, you know, forward thinking, right? So you have your emissions, you have your impacts, and the goal and the challenge, and I guess the utopian dream is more is better. higher scales, higher resolutions, longer time periods, all kinds of diagnostics to enable, should we reduce SO2? Should we not reduce SO2? Should we be looking at ammonia? Should we be worried about VOCs, right? There's a lot of diagnostics. That's the model versatility. I think RCMs, at least personally for me, flips it. It's like, how far do you want to push your model where it has yielded you sufficient outcomes to enable the policy assessments? That's where you want your models to perhaps be versatile, but not, the veracity doesn't nearly need to be as neat and clean, right? And that's where with Pavitra, for example, you back it up with a really powerful CTM, you back it up with a really powerful representative up-to-date emissions inventory, where your delta E's, your change in emissions to change in concentrations are sufficient to now start informing policy. Now, I don't care for the model to be, slow and very accurate. I just want it to be quick and efficient in being able to give these outcomes. So that's the gap RCMs fill, for health impact assessments and perhaps more. But would that necessarily at this point be able to fill a regulatory viewpoint? Perhaps not. But the end goals are so different for the CTMs and the RCMs at this point. And both are equally valuable. It's just that we really, and that's where I keep going back to this idea of, can you sequester, have a modeling clearinghouse, US EPA has it, EEA has it, right? Can we start sequestering our information in a way where we are all not reinventing the wheel? I mean, almost all modeling groups in India today, I'm a early career, addition to that here in India, but all of us reinvent the wheel in terms of infrastructure and in terms of information. So can we bring ourselves up minimally to a point where we are now adding to the science as opposed to just churning the wheel all over again? I hope that answers your question. Yes, please.
Yeah, since I was called out, I'll respond. Yeah, I mean, I don't think you really need to wait for models to take action on certain things. I mean, whether they're coarse resolution climate models or CTMs or reduced complexity models, it's not a new idea at all that black carbon reductions are kind of good policy for both air quality and climate. I mean, that's been known for probably 20 years. So I think, some of the climate modelers, like myself and others, are kind of nibbling at the edges of, is reducing black carbon going to change, 0.2 millimeters per day of rain in this specific area? There's still some decisions and some science to be figured out there, but I think the general points are well known.
Yeah, and thanks very much, Dan. Didn't mean to call you out, but definitely appreciate you putting up black carbon on the list and showing our policy brief.
Yeah, just one more point. It's like what Srinidhi said also, the same thing. But we have to keep in mind that to get to a good RCM, we need to have the CTMs running at a good confidence rate. Okay? I think that is still missing. I think that's the part where I think we have to institutionalize that capacity building at pretty much as many institutions as possible, as many heads as possible to make that. But once we are at a good confidence level, that, okay, you give me any inventory, I'm going to run this model and give you the results, then CTM comes in and does hundreds of scenarios. Sorry, RCM comes and does hundreds of scenarios.
So there are two things which I want to add on. One of them is whether concentration levels, PM 2.5 is so high, any reduction would be helpful in any ways. Second thing is that since we are discussing about CTMs, different type of CTMs, why don't all the Institute of Reputes have experiments like AQME, where you basically compare the air quality models which are used in community, and then you check what are the biases, uncertainties. It will also help you fine tune your model setups, and it will be beneficial for longer term. So, yeah.
My question is for Srinidhi. Thank you for a great presentation. Kind of the reverse of the first question that was asked. So at the end of your presentation, you mentioned some, constraints and ways to make your models better. I'm curious what kind of economic constraints are creating these model underperformances in India, whether that's like human capital, computational resources, financial resources. What kind of challenges are people experiencing?
It's, I don't want to call it relatively new, because there have been so many people, 20 years ahead who already been doing this. And it's not that work hasn't been done for India, right? It's just that it's a very steep learning curve. For anyone who's had to run a CTM on their own, it's make or break, really, in terms of your career, right? For example, I have a new lab, it's about 2+ years in. We still don't have a server setup. It's the computational needs, the kind of money that's needed to get those grants, and more importantly, finding people, especially in environmental engineering, with the kind of skill sets which are minimally needed to just be able to read the code, let alone break it, because unless you break a code, you don't get to predict. I think all of us here agree with that. It's just so immensely high. And then, especially with training, now that I'm faculty and I get to talk to students, they all want to do AI ML, right? And as appreciated as that sentiment is, you need a lot of data and a lot of really good quality data to actuate that. So right now, this balance of should we move forward, big fancy computational models, should we kind of move perhaps, I'm using this word very generously, backwards, meaning be able to use this, run RCMs, make it really quick, dirty, but useful? Or should we just put a random forest algorithm? All equally good ways forward. It's where do you decide to put the capacities in, right? Like US EPA's latest document, I think it's 2023 end, still says let's improve air mod. A Gaussian dispersion model with increasing levels of chemistry, great for up to perhaps 50 kilometers. Is that the language we want to adapt? There are no good answers. There are many wrong answers. There perhaps no collectively singular answer to that. So I would say a bigger community of people with diverse skill sets, a lot of computational folks walking into these conversations. Hey, I don't want to be building an HPC. I'm an environmental engineer, right? To be able to also train kind of this adjacent community around us to be able to support us in this work. So data analytics, yes, of course, use ML, it's beneficial. Satellites, yes, of course. Build CTMs, yes, of course. So really a big clearinghouse of many, many, many types of mathematics, because remember, no model is perfect. There are approximations. How well do you characterize that? That's on us as a community.